In this tutorial, we'll enhance our Paint app by adding new functionality that allows users to move the objects on the canvas and change their size and orientation by dragging the selection box handles. In the first part of this tutorial, we will address several critical technical challenges: correctly combining rotations and scale transformations, handling objects that are not centered on the screen, calculating rotation angles based on the mouse position, and ensuring that the selection box handles follow the object's position and orientation while maintaining a uniform size. Moving on to the second part, we will explore the app's architecture within Visual Studio Code. We will examine how the different software components of this new feature work together, providing you with a deeper understanding of their integration. So remember to like and subscribe, and let's dive in. wxWidgets offers impressive multi-platform drawing capabilities, including the ability to rotate, scale, move, and even apply a custom transformation matrix to an object. For this tutorial, you won't need to know the underlying mathematics of that process, but if you are curious, check my custom controls video, where I explain that in depth. What you need to know for now is that you can stack these transformations together. One interpretation of this transformation chain is that the object will be rotated, scaled, and then moved on the screen. The transformation matrix and its inversion can be used to convert between various coordinate systems. By calling transform point on our transformation matrix, we can convert a point from the object to the screen space. We get the conversion in the opposing direction if you use the inverse transform. You also need to know that the coordinate system starts at 0, 0 in the upper left corner of your control, so the points with negative coordinates won't be visible. Armed with this knowledge, we can start implementing our interactive transforms. The first thing we need to do is to store the current transformation. Users can perform a series of operations on an object: resize it, then rotate it, then resize it again, move, and so on. After each operation, we need to save the transformation so that the next one can be applied on top of it. We could store the transformation matrix, but that won't work if we combine rotation and scale operations. After chaining a bunch of these, we will end up with the object transformed in a weird way. Again, check my custom controls tutorial, where I explain the math of this phenomenon. So that won't work. Instead, we want to store the translation vector, rotation angle, and scale multiplier separately, and construct the transformation matrix on the fly whenever we need it. What if we have an object that's not centered at 0, 0? This rectangle starts at x 200 and y 100. We want it to rotate around its center like this, but when we apply rotation, we get a different result. That's because everything is rotated around the center of the coordinate system. To work around this issue, we need to move the object to the center, rotate it, and then move it back to its original position like this. Here's the final version of our getMatrix function that considers the rotation and scale center. Let's move on to user interactions. The simplest one is translation. We calculate the mouse movement vector and use it to translate the object. Scaling the object is more complicated. We need to measure the mouse movement projected on the object's x-axis, add it to the original half width, and divide the sum by that original value. We also do that for the object's height and multiply the resulting values by the previous scale factors. Finally, for rotations, we need a vector from the object center to the drag start point and another one from the center to the next mouse position. To calculate the angle, we use the inverse tangent of the cross product divided by the dot product. This works because the ratio simplifies to sine divided by cosine, which is the tangent. To calculate the angle value, we use the atan2 function. We need to discuss two details related to drawing handles before diving into the code. When drawing the handles, we cannot use the same matrix as we do for scaling the object. The handles need to follow the position and rotation of the selection box, but should not change their size like this. Also, we need to be careful when drawing the rotation handle. It can't change its distance to the selection box as its size changes. So with this in mind, let's jump right into the code. We store the objects the user draws in our document class, while our view handles the presentation layer. If you are not familiar with wxWidgets document view framework, I recommend my video on that topic. The document contains a vector of canvas objects, which are basically aggregates of shape and its transformation, along with the cache for bounding boxes. Our shape type is a variant of circles, paths and rectangles. Check my StudVariant tutorial if you don't know what that is. The interesting thing about our canvas object is that both the shape and the bounding box member variables are declared const. We assume that the shape never changes once created. The user can only adjust its transformation. This lets us calculate the bounding box once in a constructor and ensure it always reflects the shape, because the shape is const and never changes. In other words, we can expose the members directly and keep the class invariants intact. Let's take a closer look at the object creation process. Here, the user clicks on the canvas and moves the mouse while holding the left button. As you can see, the circle does change its radius in the process. So how can we declare it using const? The thing is, during the creation process, the canvas object does not exist yet. The view uses the shape creator object, starting the drag creation process in the mouse click handler and updating it in the drag method. Only when the user leaves the button, the canvas object is created. From this point on, the shape it contains cannot be altered. Only its transformation can be changed by the user. The shape creator class itself is simple. It contains a shape wrapped in an optional. This shape is not const. It can change because that's the purpose of this class, to handle the interactive shape creation process. The start method creates the correct shape for the currently selected tool and stores the drag start point. In the update method, we use the stdVisit idiom. For paths, we add the current point to the list. For rectangles, we change their vertices, and for circles, we update the radius. When generating the canvas object, we use stdExchange to reset the shape variable to a null optional and return its previously held value, all with a single call. This happens if the user selects the circle, path or rectangle tool and proceeds to click and drag on the canvas. However, there is another tool called transform tool. Let's get back to the code and see how we handle the click event for this one. First, we check if the user has anything selected. In this case, we want to prioritize this selection and start dragging if the clicked point is inside the selection box. Next, we check if that call was successful. If yes, then our job is done for this method. The selection box object has the isDragging flag set to true, and the actual drag process will be handled in the dragging function. Otherwise, there are two possibilities. Either we clicked on an empty space, in which case we need to reset the selection, or we clicked on another object. To answer this, we need to check all the objects starting from the top one, the R for the reverse iterator, and returning the first containing the clicked point within its bounds. Now, a lot is happening here. Bounding boxes, object spaces, object coordinates. Let's ensure we understand how these work together. As I mentioned before, affine transformations can be used to convert points and distances between coordinate systems. In our case, the screen coordinate system starts at the top left corner of our canvas and doesn't change. The object coordinate system starts at the same point but scales, rotates and moves with our shape. Notice that while the center point and the bounding box move on the screen, their positions remain constant in the object space. That's why we can store the bounding box as a constant in the canvas object class. We can also convert the clicked point to the object coordinate system. Since the bounding box is also expressed in the same system, we can check if the point is inside. If we find something, we create the selection box object, passing the found object by dereferencing the iterator. The other mouse events for the selection box are simple. We call the drag and the finish drag methods. Let's examine this mysterious selection box class, where most of the action takes place. The first unusual thing we see is the reference wrapper. We need to store the object by reference, or a pointer, for the changes to propagate to the container. And we use a reference wrapper to enable copy and move operations so that the class can be stored in stdOptional. Another interesting thing is the optional dragged element. The user can move different parts of the box, including the 5 handles and the box itself. After the user clicks on some part of the box, we want to store the dragged element so that the correct drag behavior can be used when the element is moved. Here's how scaling is done. First, we need to know which handle is being moved. Actually, we only need the handle's position relative to the object center, as this determines if we want to increase or decrease the scale. For example, moving the left handle to the left increases the object size, but the objects must shrink if we do the same with the right handle. So, considering this, we calculate the size change, divide it by the previous size, and use that value to adjust the scale. We've already talked about rotation. We need a vector from the object center to the drag start and end point. And we calculate the angle between the two using standard formulas for the cross and dot product. Finally, the translation method, which is trivial. Let's discuss our small red selection handles, as some nuances are involved in implementing these. First, the handle coordinates are described in terms of the screen coordinate system. You can see that we cleared the transformation matrix and draw the selection box using the absolute values of the handle centers. Getting the corner handle centers is easy. Convert the bounding box vertices to the screen coordinate system. The rotation handle is more tricky. We don't want the handle center to change its distance to the edge of the box when the box is resized. That would happen if we simply added some constant to the bottom line, like this. That absolute distance would be scaled with the object, so what we do here is we counter that scaling by dividing the constant by the scale factor. The toScreen coordinates method will multiply it again, and the scale effects will cancel out. Alright, back to our drawing method. After drawing the box, we proceed to draw the handles. Again, we need to be careful. We want our squares to rotate with the selection box, but we don't want them to scale. That's why we use only the rotation part when constructing the transformation matrix. Additionally, we translate by the handle center to simplify the draw rectangle call. This also affects our handle hit tests. Like with the object click tests, we construct a matrix to convert a point on the screen to the handle coordinate system and check if the square contains the transformed point. That's it for the interactions. We just need to draw everything on the screen and properly serialize our transformations. The onDraw method in the View class delegates work to its components. Objects know how to draw shapes with the correct transformation. The selection box draws handles and the selection rectangle, and the shape creator takes care of the shape in construction. Finally, serialization. This is really simple. We write and read the data represented by the transformation class. With all these changes, our app is starting to be useful. Now we need the undo stack, drag and drop for bitmaps, and some layer support, and we can make Adobe Illustrator obsolete. Thanks for watching.